Welcome back and all. As I told you in an email that I sent out, I will not be here starting Friday. So the last two classes, the Friday class will be a videotape, which you can either watch in this room or you can watch online, linked to the schedule page. It will be a review of the semester. It's actually a review of the semester from last year. And Monday, there's no class at all. And I won't be able to hold office hours next week either. I'll simply be out of town. And the final exam will be given by someone else. I mean, my exam, someone else will be looking after it. The final exam is 60 questions, multiple choice, same as it has been for a long time. As always, I encourage you to take the old final exams as preparation for this and try to learn from those exams. Any questions about, yeah? The final review will be Friday, and it will be last year's review, which was decent. I watched it to make sure, it's okay. Pretty much same stuff. All right. Other questions? Yeah, I edited the syllabus, as I've been doing all along, a little bit. All right. I'll remind you now, bring a pencil to the final. What else? Anything else? Oh, it'll cover, we'll get as far as, and no further than musical instruments between today and Wednesday. That'll be enough. So the very last topic sometimes happens, sometimes doesn't, is ocean waves and seashore and stuff, and I won't get there. Okay.
Good today.
All right? All right. So last time, content-wise, I was talking about how clocks work. And clocks, virtually all clocks that you have yourself are based on harmonic oscillators. And I'll just remind you again what harmonic oscillators, it is a system that has a stable equilibrium, and that when pulled away from stable equilibrium, it experiences a restoring force or something equivalent to a force that's proportional to how far you pulled it away. And the classic harmonic oscillator is an object on a spring. So the object provides an inertial component, a mass, that tries to go straight, and the spring supplies the right restoring force, a restoring force that's proportional to displacement. And so masses on springs act as harmonic oscillators. They have the right characteristics. And what you get when you have a harmonic oscillator is you get a system that has a period of oscillation. That is the time it takes to go through one cycle. It doesn't depend on how big that cycle is, what is known as its amplitude. So the amplitude of the oscillation, its extent, typically that's a spatial extent, how big it is, that doesn't matter. You get the same period anyway. And okay, why? It's because when the motion gets larger, more extensive, bigger amplitude, that by itself would make things take longer. However, the restoring force, gets larger to match it. So bigger motions, they just move faster. It still goes through the motion the same amount of time. And harmonic oscillators are great as timekeepers for clocks. They tick off time very steadily, and you don't have to be super careful about how big the motion is. You get the same period anyway. The tick is steady. You can count the ticks, and you can watch the passage of time. Any thoughts or questions about harmonic oscillators themselves? Okay. Musical instruments are going to be in the next step along with harmonic oscillators. They're still harmonic oscillators. Why would you care that they would be harmonic oscillators? Because when you play a musical instrument, you get a certain sound out of it, typically. Often you describe it as a pitch. And the pitch doesn't depend on the extent of the motion. Whether it's loud or soft, most musical instruments produce the same pitch, all else being left alone. And that's kind of nice. You don't have to adjust when you're playing a guitar or a flute or whatever conventional, particularly Western instruments. You don't have to compensate for how loud you're playing. Loud or soft, you get the same pitch in many sorts of things. Hopefully that's familiar to some of you who play musical instruments. All right, so story of musical instruments. Just because they're harmonic oscillators. Oscillators doesn't mean they're as simple as some of the ones I was doing previously. Okay, so just a question to think about here is that when you tap a wine glass, you get a characteristic sound out of it. Right? And the question is, if you wanted to break that glass with sound, you want to choose a glass with, and the choices are a long decay time. You heard that the sound decayed slowly. You hear it would make a tone for quite a long time. So do you want a glass with a long decay time, short decay time? Those are the two choices in decay time. And the other is whether you want to expose it to the sound that it likes to make, its characteristic tone, or to just a sudden sound. You okay with the question? You're trying to break a wine glass. What kind of wine glass do you choose? One that has a long decay or a slow decay? Sorry, a long decay or a short decay. A short decay would be ding, ding, and then gone. And, okay, so how many think you want a long decay and the characteristic tone? Expose it to the characteristic tone. How many think you want a short decay and expose it to the characteristic tone? How about long decay and expose it to a sudden sound? Last choice is short decay and expose it to a sudden sound. Man, we're getting, it's pretty flat. You know, you've got about 25% across the entire range of choices. As in, it's potluck, who knows at this point. Okay? We are headed towards breaking a glass, as you might expect. We'll do it. Okay. So, some observations about musical instruments. They can produce different notes. And just we'll get a little language about notes. And the words of music and the words of physics are not necessarily identical, but they're very closely related. They have to be tuned to produce the right notes. And what is tuning doing? Different musical instruments sound different, even when they're producing the same notes. And a little bit of where does that come from? And finally, they require energy to produce sound. So sound carries with it energy. And how does that energy sort of move through the system? I've harped on the fact all semester that watching the flow of energy through a system, or actually any of the conserved quantities, often gives you a lot of information about them, and so we'll watch energy go through the system. All right, so I got a whole bunch of questions to go after that probably will keep us occupied for the next two classes. So then the first one is, why does a taut string have a specific pitch? So I'm thinking in terms of a violin. This is the world's least expensive violin. So what gives that string its pitch? And that's the question. I think I paid $50 for that violin. I hesitate to think who made it, the poor person. Probably 5 years old. All right, anyway, I provided an income. So why the basic pitch? Well, it turns out the taut string is a harmonic oscillator. It has the required, it meets the requirements. So a taut string, and by taut I mean that you put tension in it. You pull one end of the string one direction, one end of the string the other direction. Can I bring it up with me? Yeah. For fun, I have it. So this is my equivalent of a string. It happens to be a spring for reasons that you'll see in a moment. But if it's just loose, it doesn't have any particular interesting behavior. But if I pull on it and make it taut, it can do a motion like this. You see a motion? That motion up and down is the motion of a harmonic oscillator. And the fact that it is a spring makes it kind of make some sense that if I pull it likes to be straight. When I pull on it, if I pull with my right hand, or as you see on the left, if I pull the left to the left and the right to the right, I create tension in this string or spring, whichever you like. And that tension gives it an equilibrium shape. It wants to be straight. That, when it is straight, it is that then and only then can the various pieces of it experience zero net force and be at equilibrium. Gravity is making a little complexity to this. Gravity bends it downward a little, but not much. It's pretty straight. We can pretend gravity doesn't exist, and we won't lose anything the story. So let's just pretend gravity's not here. Pulling on it and putting tension into the string, or giving it a tension, pulling it taut, gives it an equilibrium shape, straight. If I distort it away from equilibrium, I'm out of hand, so okay. If I do this, there, right, fire my glasses into the ceiling. So if I do this, it's experiencing restoring forces, and without my neck, being there, it's gonna go up through straight. And you also notice that when I let it go through straight, it went back to straight. It was very happy to get there, but when it arrived, it was moving, and it overshot, and it bounced up and down, right? That's like the motion of a harmonic oscillator. It has the right sort of restoring force to be a harmonic oscillator. The restoring force is proportional to how far you take it away from center. Is that okay? So it has an inertial aspect. So just to follow the story up here that I've got. First off, it has a stable equilibrium. It happens to be a straight line is a stable equilibrium for a taut string. It has a mass that provides an inertial aspect, the tendency to keep doing what it was doing. It wants to keep moving in the direction it was moving. But it also, between its tension and its length, when you pull it out of straight, it has an arc to it as a result. And that arc results in each portion of the string or spring experiencing a force back towards center. And that force gets stronger and stronger as the distortion of the thing gets greater and greater. And it follows the rules. It's spring-like. The restoring force is proportional to displacement. Any questions about why it's a harmonic oscillator? Or issues like that? Okay. So the fact that it's a harmonic oscillator means that it has a period of motion. First of all, it's got a motion, a cyclic motion. In this case, it's a dance around straight. And the dance, I should also point out, the dances I'm going to show you, are they strictly vertical? Now, it doesn't actually matter whether the dance is up and down, this is pure up and down, or toward you or away from you. They actually have the same period. If I put the tension matters. So if I change the tension, I get a different period. But what I want to do is whether the thing is going toward you or back and forth this way, back and forth this way, or back and forth this way, or both at once to an extent, it's still a harmonic oscillator. There's some more complexity to this harmonic oscillator than we're used to. It's not so wildly different than, say, the bowling ball pendulum that I have here periodically. That can swing left-right, it can swing toward you, away from you. It's got some complication to it too. This, as it turns out, will have more complication by far than the bowling ball pendulum, but we're sort of getting on track here. You gotta walk before you run. So, what I want to do, back there. I'm going to make that string, or a rope. There's a rope that stretches from the left side to the right side. It has a fairly constant tension introduced in it by a weight hanging off on the right over on this side. And I want to turn off some of the lights. Turn off that. And I want to dim the room lights. I'm going to make that string begin to there we go. It's dancing up and down, and the point of the flash is to show you the arc. It's timed right now a little oddly. Can I change the timing of that? Not easily. Let me turn the lights back on. But you can see it. You can see the shape pretty well anyway. You see it goes from an arc up to an arc down and back and forth. It's going, is it mostly vertical? It's mostly vertical. What about that arc? It happens to be shaped according to the trigonometric sine function. Remember that from way back? It's it goes from the sine function of angle 0 is 0. The sine function of angle, you can call it 180 degrees, or 180 degrees, or alternatively pi in units known as radians. This is sine of angle, and in the middle where you're at 90 degrees or pi over 2, it's 1. Sine is big there. It's small at the two ends. If it doesn't that's not familiar, don't worry about it. The point is, this dancing motion is a type of wave. It's called a standing wave. It looks a lot like a wave, right? It's a wave that doesn't move left, right. It's dancing in place. And this sort of motion has, for this particular one, has 2 points that don't move for all practical purposes. The ends. They're known technically as nodes. Let me show you. They're known as nodes. And, of course, we're blocking the view of that. Plan ahead. And in the middle, where it's moving the most, is a place that's known as an antinode. So nodes are places of where some physical quantity is 0, and an antinode is some place where some physical quantity associated with the rhythmic motion is maximum. So there's one antinode, 2 nodes. Okay, let me stop this crazy thing. So the wave that dances in place, it has the characteristics of a harmonic oscillator, so its period of motion doesn't depend on how big the motion is. If I made this vibrate more strongly, less strongly, it doesn't matter. As long as I was driving it at a particular rhythm to get it moving. I was shaking it up and down. It's the equivalent of me shaking my hand to make this thing go. This is the rhythm it wants to do. I don't have a lot of choice. I do secretly, if I pull it tauter, I can make it go faster. That's too fast. I can't even make it go. Right? That's faster. If I go less taut, it goes slow. You've done this with jump rope. I hope people still play jump rope, right? You can choose how fast it skips by how taut you make that rope. What you're doing when you play with that, let me give you some words here. I talked about period, which is the time it takes to go through one cycle. And I talked about amplitude, which is how big the motion is as it goes through. We'll see that amplitude is associated with loudness. So bigger amplitude motions in musical instruments typically relate to louder sounds. So that's one observation. Another observation on this slide that I want to not leave behind is that with musical instruments, rather than talking about how long it takes to go through a cycle, when the cycles get very fast, you start talking about how many cycles occur every second. It's the reciprocal of period. So instead of talking about period, which is 10 seconds, 20 seconds, 50 seconds, long cycles are nicely described in terms of period. Let's talk about 1 over period, which is how many cycles occur per second. Period is seconds per cycle. The reciprocal of seconds per cycle is cycles per second, also known as frequency. So the word I'm trying to introduce here, wandering around, is frequency. It's the measure of how many cycles occur per second. And as the period gets shorter, the frequency, as the period gets smaller, the frequency gets larger. They're reciprocals of each other, 1 over each other. So as the period gets, so this is like this is a 1 second period about. 1/1000. That's about a half-second period. Go 1 second. Too boring. I can't do 1 second. So this is about 2. This is a half a second per cycle. The period's half a second. It's also 2 cycles per second. That's the frequency. Is that okay? This maybe 8 cycles per second, something like that. And by the time you get up to about 20 cycles per second, if it's moving the air, you'll begin to hear it. A very low-pitched sound. That's where pitch comes in. Pitch is the musical equivalent to frequency. The faster the motion gets, the higher the frequency is, and also the higher the pitch is, what you hear with your ears. And we can hear motions, we hear the sound produced by motions that occur at frequencies, or equivalently pitches, of about 20 cycles per second, up to maybe 20,000 cycles per second when you're young. With age, most people lose the high end, the high pitches. Last time I measured my own hearing, I could hear above 11,000. I couldn't hear much above that. That was my limit. You're somewhere on that path, probably. All right. So with that, any questions about period, frequency? Yeah. Pitch is equivalent to frequency. So a low pitch note. This is I don't know what that is. 100 cycles per second, and then that's a higher pitch, higher frequency. I can do it this way. Can you hear that sound? That's 128 cycles per second. This is 384. Okay? Fingers on the chalkboard? No, won't do that. All right. Does a recording of fingers on a chalkboard, is that just as irritating as the real thing? You need a YouTube video, right? It'll go antiviral. Things to send your friends and annoy them. So when you have a yeah, I expected every. All right. The pitch of a vibrating string is determined then by an inertial part and a restoring force part. The inertial part is just going to be the mass of whatever's moving. The restoring force part is going to be in part the tension. The more taut you pull that string, the more vigorously it fights to be straight. But also the length matters, because a very long string doesn't you can move it off center without much distortion, relatively speaking, because it's so long it barely even knows it's not straight anymore. But a very short string, you take it a tiny distance off center, and it's now seriously distorted. So length matters. And finally, the pitch of the motion, that's this simple motion, which I'll begin to name. I'll call it the fundamental vibrational mode of the string. The pitch depends on the tension. That is, the more tension, the higher the pitch. Equivalently, the higher the frequency. You pull that string tauter and tauter, and it goes faster and faster, because the restoring force gets stronger. It also depends on 1 over the length, which means the shorter the string, the more vigorously it pulls back towards center, and therefore the higher the pitch. And lastly, 1 over the mass. As you reduce the mass of the string, it goes through its motion faster, because it's more susceptible to the pushes of the restoring force. So the pitch of the string, equivalent to the frequency of the string, is proportional to tension. It turns out to the 1/2 power. 1 over length and 1 over mass to the 1/2 power. The 1/2 power is a detail. It's interesting, but I won't worry about it too much. The main thing is that you realize tighter string, shorter string, lower mass string, all of these make it go faster. It goes through its motion more times per second, you get a higher pitch. Is that okay with everybody? Or questions about that? Why that happens? So if I were to add weight to this string so that the tension increased, that motion I showed you would occur at a higher frequency. So more tension. If I shortened the string, I instead of having it 10 feet long, 3 meters long, if I made it 1 meter, it would go faster. And lastly, if instead of having a string that was as thick as that one is, we went to a much thinner string with less mass, it would go faster as well. And this explains to an extent why the physics of a violin. A violin has 4 strings, just like a guitar, same idea. And the lowest pitch strings are both the least taut strings. They have lower tension, and they have greater mass. To start with, they're the same length. The length that matters is from here, where the string touches to here where the string touches. That is the length. It's defined by two structures on the violin, similarly on a guitar. And the basic pitches then of these strings are determined by the tension and the mass. And the low pitch string has a lot of mass and not much tension. You can hear a little bit of a shift in pitch. The volume goes, you hear that? Can you hear that? That's the slight failure of it being a harmonic oscillator. It's not quite a harmonic oscillator. It's very close, but not quite. When I'm pulling it badly out of shape, it pitch rises a little bit, which indicates that it's not quite, the restoring force isn't quite proportional to how far I distort it. It's close. But anyway, the main point I want to do is, this is low pitch. The string on the other side, which is much thinner, less mass, and much tauter, has a much bigger, so it's got a bigger restoring force. Oops. Twang city. Higher pitch. Low pitch. It's not tuned, of course. You okay? Why the difference in pitch? I tuned it. What do you want for 50 bucks? Anyway, so to begin with, to choose the pitches, you choose the mass of the string. It's actually the mass per portion of length. So you buy a heavy massive string for the low pitches, a thin, easily accelerated string for the high pitches. You then adjust the tension correctly before the concert begins with tuning pegs and adjusters to get the right tension so that the string at full length has the right pitch. And during play, when you're playing it, you change the length on the fly by shortening the string with your finger. You press it against the fingerboard, and that shortens the string. So if I start with the string, the big string, that's its normal pitch. But if I shorten it, I make the pitch higher. Come on. I'm not a violinist, I'm a pianist, so you can reach inside and play with the strings of the piano. But I've never done that. All right. Look, it broke. So you're okay with the basis for adjusting the pitches of a simple stringed instrument. Choose the mass, choose the length, choose the tension, you get a pitch. Sort of all there is to it. Except, this is what's known as the fundamental vibration. When the string vibrates as a single arc, up and down. But that's not the only way it can vibrate. Any object that has multiple components that can move to some extent independently of one another can vibrate in more complicated ways than just its fundamental pitch, fundamental mode. It can also vibrate in other modes. And I can show you one here. So this is the fundamental mode. But if I go faster, come on, I'm going too fast. I got to practice on this because I'm going to be using one when I'm out of town. I can't take all my gadgets with me. Come on. I'll cheat. I need more practice. Practice, practice, practice. That's how to get to Carnegie Hall, right? All right. That's the fundamental vibrational mode. You see its period. It takes a third of a second, maybe. Equivalently, it has a frequency of about 3 cycles per second. Let's see what happens when we go to about 6 cycles per second of shaking. A second harmonic mode. This is This is another way in which the string can vibrate as another harmonic oscillator. Well, yeah, I turn away, things go to pieces on me. There we go. Stay. Oh, come on. There it is again. It's vibrating as two half-length strings. And the tension is the same. The mass is effectively unchanged. We haven't changed the string, but we've halved its effective length. It's vibrating as though it were only half as long as it used to be. The middle point is now a third node. It has three nodes. One at this end, one at that end, and one in the middle. Three nodes. And it has two antinodes. One here and one equivalently over there. So this is... I'll stop it for a second so I can say what I want to say. Complicated systems like this. So systems that have an extent, they happen to be systems that have an extent but that are limited. They don't go on forever. First off, they have vibrations, rhythmic systems that vibrate that are standing waves as opposed to traveling waves. We'll see, which I won't get to. On the ocean, which in effect goes on forever, the basic modes in which it can vibrate are traveling waves. They move. They go across the ocean, and you watch them go by. In systems that have an extent but end like the string, it's not like the ocean. It doesn't go on forever. It just stops. The most basic ways in which that can vibrate are standing waves. They're waves that don't go anywhere. They dance in place. And you've seen dancing waves on things. You can see them on a glass of water when something's vibrating. You look in, you see a pattern on the surface of the water. I hope you've seen that. There's dancing there. When you start water sloshing in a bathtub or a basin, it's going up and down. It's another standing wave. Standing waves are all over the place in limited but extended objects. Here, this has standing waves in it, and I'm showing you the first and second possible standing waves. The lowest frequency one was the fundamental. I showed you that single arc. The next lowest frequency one was the two half strings. And in musical instruments, these have associated with them pitches. And the pitch of the fundamental motion is just the fundamental. It's called the fundamental pitch. And so the fundamental pitch of, pick any instrument. Is that really the fundamental? I'm touching the toes. That's the fundamental. But that's not the only way in which it can vibrate. That or the string. Actually, just to show you. Do you hear that sound? That's the fundamental. That's not the fundamental. Okay? So the point of doing this, and we'll come back to that one. These other ways in which an extended system can vibrate are known as overtones in general, because they all have pitches that are higher than the fundamental, so they're over. They're over the fundamental tone. In music, most musical instruments, the overtones are special. They're a special range of possibilities. Most musical instruments are linear systems. They have one important dimension. The string has one important dimension from left to right. Nothing else much matters. A pipe has one important dimension from left to right in this case, or top to bottom. One important dimension. When you have one important dimension, the overtones are special for reasons that have mostly to do with mathematics. The overtones are integer multiples of the fundamental frequency or pitch. So they're known as harmonics rather than just generic overtones. Overtones can be all over the place. Harmonics are special. They're multiples of the fundamental tone. So that's why when I started this guy vibrating, and at the fundamental, where is that guy again? There's the fundamental. That, not only is it the fundamental, you're seeing spatially the fundamental mode of vibration, but the pitch associated with it is the fundamental pitch. If I go to twice the fundamental pitch, I will get the what's called the second harmonic mode of vibration, which is the 2 half strings. So I go to twice the pitch. There it is. That's, the name for that is the second harmonic. Is there a third harmonic? Sure. It's at 3 times the fundamental pitch. And how about 4th harmonic? And 5th harmonic. You get the idea, right? Ah, it's going to explode. All right. So what are the takeaways with this? For a single string with a single mass, a single length, a single tension has a well-defined pitch for its fundamental vibration. But that's not the only way it can vibrate. It can vibrate not only the fundamental, but at twice the fundamental as 2 half strings, or 3 times the fundamental as 3 1/3 strings, and so on. And it can do them all at once. It doesn't have to do just one of those. I can't make them happen here, but when you play a violin or guitar or pluck it or bow it, whatever, depending on where you interact with that string, you can get it moving in a mixture of those motions simultaneously. And your ears will hear this. Your ears will hear that it's both that it's not just the fundamental pitch that I'm hearing. I'm hearing some of the harmonics. They incidentally sound good with one another, at least to the Western ear. The difference between the fundamental and twice the fundamental, which is the second harmonic, is in musical notation is the octave. That's the difference between, say, middle C and high C. 1 octave. That's a factor of 2 in frequency, and it sounds so. Our ears hear it almost like the same note. We interpret them. This is how you get people with different voices, soprano and a bass singing together. They will sing in unison. They'll be singing notes that are related by factors of 2. Those are octaves apart. They are like the fundamental and the second harmonic. The third harmonic, which is a factor of 3 over the fundamental, is the octave in the 5th. For those of you who don't use it. So it's ba ba that's 1. That's 2. It's hard to do when you got a cold. Chronic. It's your fault. And then if you go up, the 4th harmonic is the second octave up. So if you get somebody with 5 octave range, which is not me, they can go through all these factors of 2 and 3 and whatever. What else? Okay. So part of how you interpret, how you identify instruments is by listening not just for the pitch that their fundamental vibration is making, but the mixture of the other harmonics, typically, that are present in the sound. When it's vibrating, not just as a single string going up and down, but as the 2 half strings, if it's a stringed instrument, as 3 1/3 strings, and so it does a little bit of that all at once. Is that okay? What I want to go to next, so not to leave it in the dust, is this one. How do you get the string vibrating in a violin? Well, and I didn't bring the bowling ball pendulum out here, but there are really 2 main ways in which instruments get the motion going. One is by just giving the vibrating system, say a string, one sudden push. For example, plucking the string. Yeah, I should have tightened that anyways. So when you do that, I'm giving it all the energy in a single effort. I grab the string, I pull it off center, an action which requires work, and gives energy to the string, and then the energy is present in the motion, and it keeps moving until it gets rid of that excess energy. We've seen that before, that oscillators in general, and harmonic oscillators in particular, they continue to move until they get rid of the one conserved quantity that they can't get rid of easily, energy. So you can give them all the energy at once, or you can give them rhythmic pushes. You give them pushes in sync with their motion, a little bit each time. They will manage to build up a big motion. I don't have a bow. The bow with my very, very simple violin broke years ago. So what a bow does, in contrast to plucking the string, the bow gives rhythmic pushes to the string. The details of how that's done are not so important. It happens to do with horsehair and rosin and the motion of the string, that the bow manages to grab the string once per cycle and give it a little shove, and then let it go through its motion, and then give it a little shove, and go through its motion, and give it a little shove, and the shoves are always in the right direction to give it a little, do a little work on it, add a little energy to it. So that rhythmic pushing of the bow manages to get the string vibrating vigorously, and it's different. It's a continual addition of energy. The bow, the string can continue to make sound as long as somebody keeps doing work on it with the help of the bow. And what that brings us to is an interesting way of transferring energy from one object to another. In this case, from the bow to the string. It's in sync with the motion of the object itself. It's known as resonant energy transfer. And just to give you a visual example of resonant energy transfer, here are two pendulums, same length, same gravity. They have the same period, right? Remember the length of a pendulum and the strength of gravity are all the determinants period. So these two pendulums are identical. They're connected in this case by a very wimpy spring. And if I get this one moving, it will give little pushes to that one as it moves. Let me try it. So I never touched the pendulum on the right, but look what's happening to the pendulum on the right. The rhythmic pushes, in sync with its own natural motion, transfer energy from the pendulum on the left to the pendulum on the right by resonant energy transfer. And the pendulum on the right now has almost all of the energy. The original pendulum is almost at rest. In fact, right now it's at rest. That's the moving one. And now what's going to happen? You're going to come back. You've seen or heard this kind of effect in real life often. When music is playing on your sound system and objects in the room begin to vibrate, you hear them making sound. They're having energy pumped into them rhythmically in sync with their own natural motion by resonant energy transfer. So this is the sound system. This is the object off in the corner of the room getting rhythmic pushes. And it goes a little more until it's really going strongly. Does that make sense? And the bow does this. The bow does it intelligently, so it's actually watching the motion of the thing it's pushing on, and it rhythmically pushes it, just in sync with its motion. And that detail I won't worry about at the moment. What I do want to worry about is if you can transfer energy a little at a time by giving something a rhythmic push in sync with its own natural resonance, its natural rhythm. Can you break a wine glass that way? Right? So remember this question. So you tap a wine glass, it makes a sound. Now I want to try to break the wine glass and think resonant energy transfer, giving energy in sync with the natural motion. If you want the wine glass to accumulate lots of energy by little rhythmic pushes from, for example, sound, how do you want to convey the energy into the wine glass? I mean, I haven't built up to this totally well, but it's decent where it's about the right time of the hour. So you okay with the question? How many think you want to expose the wine glass? First, you want to take a wine glass with a long decay, one that holds its energy well, and expose it to its characteristic tone, its own fundamental vibrational mode. How about the short decay, one that doesn't hold its energy well, and expose it to its own fundamental vibration? Okay? How about the long decay, one that holds its energy well and expose it to a sudden sound? And how about short decay and sudden sound? Okay, you guys have swung pretty hard over towards what I wanted to see, which is yes, you want to expose the wine glass. First of all, you want to choose a wine glass that holds energy well. That has a long decay, that holds on to the energy, goes through rhythmic motion for a long time before coming to rest. And you want to expose it to that sound that it makes, because that you will get it going. This is what I'm doing here. When I'm shaking this thing, I'm shaking it at its natural resonance, or trying to. And when I hit that natural resonance, it starts going like crazy. So let's do that with sound. To do this, we can look down on this glass. There's a glass in here. And if we look down on the rim of the glass from above, that will appear. Yes. You're now looking down on the glass. And we've got a strobe light so we can watch the glass at the same moment per cycle. And what you will see as I make the machine start whistling at it loudly, and it gets quite loud. Eventually it'll get quite loud. You will see that its fundamental vibrational mode is a distortion of the ring. It's not a string after all. It's more complicated. But the motion will be oval one direction and then oval the other direction, back and forth. It's going to go out of round to ovals as you look down on it. And it gets loud even for me. Okay, so we want to go to strobe on, right? Turn the strobe on. I'm going to start going up in amplitude. What you're seeing with the straw bouncing around is that tone is really getting the attention of the glass. And now I'm going to adjust the frequency a little bit to try to hit the... I'm trying to hit the resonance. Sorry about the sound. And now I'm going to go from full volume. Playing with the frequency track. There we go. So apparently some of the great opera stars, Caruso, for example, could hold a wine glass in his hand and break it with sound. To do that, he had to sing at the right note, right on the pitch of the natural resonance of the glass. And he had to get his own amplitude up high enough that the energy was going in rhythmically with every cycle, more energy, until finally he broke the glass. So, thanks. Anyway, see you on Wednesday.